A spacecraft built in 1977 is currently dying in the darkness between the stars, and NASA just sent it a lifeline from Earth. The problem is that the signal takes almost 24 hours to arrive one way. So engineers sent a command, then waited 2 full days just to find out if it worked. That spacecraft is Voyager 1. It is the most distant human-made object ever built. It is sending back data right now as you watch this. And what is happening to it, and what NASA just pulled off to keep it alive, is one of the most remarkable stories in the history of space exploration. Subscribe now so you do not miss what comes next, because this mission is in its final chapter, and every update matters. Let me take you through all of it. Voyager 1 was launched on September 5th, 1977. It left a Florida launch pad, flew past Jupiter in 1979, past Saturn in 1980, and then just kept going. No brakes, no destination, just outward, into the dark, forever. It was designed for a 4-year mission. It is still operating 48 years later. In 2012, Voyager 1 did something no object built by human hands had ever done. It crossed the heliopause, the boundary where the sun's solar wind loses its grip and the true interstellar medium begins. It left the bubble of influence created by our sun and entered the space between the stars. At that moment, it became the first human-made object in interstellar space. There was nothing out there, no planets, no warmth from the sun, just the thinnest possible fog of plasma, ionized gas ejected by dying stars millions of years ago, and magnetic fields that have nothing to do with our sun. Voyager 1 is floating in that void right now, more than 15.8 billion miles from Earth, measuring a region of the universe that no other instrument has ever touched, and it is running out of power. Here is how Voyager 1 generates electricity. It does not have solar panels. At those distances, sunlight is so weak that solar panels would be useless. Instead, it runs on 3 radioisotope thermoelectric generators called RTGs. These devices use the heat produced by decaying plutonium-238 to generate electricity. When Voyager 1 launched, those RTGs produced about 470 watts. They have been losing about 4 watts per year ever since, as the plutonium slowly decays. As of now, in 2026, those generators are producing less than half of their original output. Less than half. After 48 years, the power source that has kept this spacecraft alive is running down, and there is nothing anyone can do to stop it. This is not a surprise to NASA. It has been expected for decades. The Voyager mission teams have been planning for this moment for years, carefully drawing up a ranked list of which instruments to shut down and in what order, making calculated sacrifices to keep the spacecraft functioning as long as possible. But even with all that planning, the last year has brought moments of genuine crisis. Moments where Voyager 1 came uncomfortably close to going silent forever. On February 25th, 2025, NASA shut down the cosmic ray subsystem on Voyager 1. This was a trio of telescopes that had spent decades measuring high-energy particles streaming in from the sun, from the galaxy, and from beyond. It had been running almost without interruption since 1977. In one command, sent across 15 billion miles of space, it was switched off permanently. The reason was simple. Electrical power is running too low. Suzanne Dodd, the Voyager project manager at NASA's Jet Propulsion Laboratory, put it plainly. She said if they did not turn off an instrument on each Voyager, the probes would probably have only a few more months of power before they would need to declare end of mission. End of mission. That is what we are dealing with. 2 days later, on February 27th, 2025, something happened that was not planned. During a routine, pre-scheduled roll maneuver, Voyager 1's power levels dropped unexpectedly. A roll maneuver is when the spacecraft rotates to keep its antenna pointed toward Earth. It is something Voyager does regularly. But during this particular maneuver, the voltage fell to a level that came dangerously close to triggering something called the undervoltage fault protection system. That is an automatic emergency response built into the spacecraft that would start shutting down components on its own. Not in the careful, controlled order the team had planned, but automatically, without human direction. And recovering from that kind of automatic shutdown at a distance of 15 billion miles is a lengthy process that carries its own serious risks. The team reacted immediately. They acted before the spacecraft acted for them. But the February 27th scare was a warning. The margins are this thin. A routine maneuver nearly triggered an emergency. This is the state Voyager 1 is in. After the February events, NASA knew they had to act faster than planned. On April 17, 2026, engineers at JPL sent another command across billions of miles of space. It took about 23 hours to arrive. Then it took 3 hours and 15 minutes to execute. And when it was done, Voyager 1's low-energy charged particles experiment, a device that had been running almost without interruption since 1977 across nearly 49 years and over 8.5 million steps of its internal motor, went dark. The principal investigator for that instrument was Stimatios Krimagis from the Johns Hopkins Applied Physics Laboratory. He wrote about the shutdown in an email. He said the stepper had worked flawlessly for nearly 49 years and over 8.5 million steps. He said it kept working even after they turned off its supplemental heater to save power, and its temperature dropped to minus 62 degrees centigrade. He wrote, "This is the stuff that dreams are made of." That is the scientist whose instrument just got turned off for the last time, talking about what it accomplished. Minus 62 degrees centigrade, still working, for 49 years. After the LECP shut down, Voyager 1 was left with just two functioning science instruments, the magnetometer, which measures the magnetic field of the interstellar medium, and the plasma wave subsystem, which detects the vibrations of plasma. It can be used to measure the density of the interstellar gas Voyager moves through. Of the 10 original instrument packages that launched in 1977, 7 are now turned off. 7. And here is what the team estimated. Shutting down the LECP buys roughly one more year of operating headroom for those two remaining instruments. 1 year. That's the margin they are working with. But the story does not end there, because NASA is not giving up. They are not sending Voyager into the dark without a fight. For months, engineers at JPL had been quietly working on something they internally nicknamed the Big Bang. That name tells you something about how the team views it. It is not a small adjustment. It is not tweaking one setting. The Big Bang is a sweeping, all-at-once reconfiguration of how the spacecraft manages its power, turning off specific powered devices and substituting them with lower power alternatives, all in a single coordinated command sequence, while maintaining the critical balance of keeping the spacecraft warm enough to keep functioning in the deep cold of interstellar space. That last part, warmth, is not a minor concern. Voyager 1 is in interstellar space where the temperature is close to absolute zero. The only thing keeping certain components from freezing solid is the heat generated by the spacecraft's own instruments and systems. Turn off the wrong thing at the wrong time and fuel lines could freeze. If the fuel lines freeze, Voyager 1 loses the ability to point its antenna toward Earth. And if the antenna no longer points at Earth, the signal stops. The mission ends, not with a final data transmission and a clean shutdown, but with silence. This is the tightrope the team is walking. Every watt counts, every degree of temperature counts. And they are doing all of this from California, sending commands that take nearly 24 hours to cross the distance and waiting another 24 hours for any response. A 2-day round trip for every decision. Because the stakes were so high, NASA decided to test the Big Bang on Voyager 2 first. Voyager 2 launched 16 days before Voyager 1, back in 1977. It took a different path through the outer solar system, flying past Jupiter, Saturn, Uranus, and Neptune before heading outward. It crossed into interstellar space in November 2018, more than 6 years after Voyager 1. Right now, Voyager 2 is about 13 billion miles from Earth, closer than Voyager 1, which makes the signal delay slightly shorter at about 19.5 hours one way, compared to nearly 24 hours for Voyager 1. Voyager 2 went through its own sequence of instrument shutdowns. Its low-energy charged particles experiment was switched off in March 2025. Like Voyager 1, it was left with 3 functioning science instruments and a power budget that was shrinking every year. Then came the Big Bang. Engineers spent months in late 2025 and early 2026 thinking through the procedure. The idea was to simultaneously switch off 3 specific devices, including an old tape recorder and 2 heaters, while turning on 3 different ones, 2 different heaters and a propulsion-related instrument, in a carefully choreographed sequence that reduces overall power demand by close to 10 watts per year, without any critical components getting too cold. Kareem Badarudin, the Voyager mission manager at JPL, said they could not afford to be wrong. He said the procedure was risky. He said everything on the spacecraft functions as a heater, no matter what it was originally designed to do. The engineers spent months working through every possible failure mode before they were ready. The test on Voyager 2 was scheduled in stages. NASA confirmed on August 4th, 2026, just days ago, that the Big Bang maneuver on Voyager 2 was a success. All 3 of Voyager 2's remaining science instruments will keep running for at least 1 additional year. Without the maneuver, the mission would have had to shut off another instrument before the end of 2026. That instrument would have been gone forever. No other spacecraft currently operates in interstellar space. The data that Voyager 2's instruments collect cannot be collected by anything else. But Rudin said, and this is a direct quote, he did not want to jinx it, but the Big Bang test had gone remarkably smoothly. That's the reaction of someone who has been holding their breath for a long time. Now the team is preparing to perform the same procedure on Voyager 1. A power test on Voyager 1 was successfully completed at the end of July 2026. The thermal test, verifying that the spacecraft can stay warm enough through the procedure, is scheduled for the end of August, subject to change based on data analysis. If both tests pass, the Big Bang will be attempted on Voyager 1 in the coming months. If it works, NASA says there is even a possibility of restarting the low-energy charged particles experiment on Voyager 1, the instrument that was shut down in April. It is still physically there. Its motor is still running. One part was left partially active as a contingency. If the power situation improves enough, it could come back online. That is what the team is working toward, not just survival, a possible revival. Now step back from the engineering story for a moment and think about what Voyager 1 is doing out there in the dark between the stars, and why losing it would be genuinely irreplaceable. Voyager 1 is the only instrument humanity has ever placed in interstellar space. When it crossed the heliopause in 2012, it entered a region that had never been directly measured by anything humans built. Before Voyager 1, everything we knew about the interstellar medium, the plasma, the magnetic fields, the cosmic rays, the density of the gas between stars, came from observations made from inside the solar system, interpreted through models and indirect measurements. Voyager 1 changed that. It started sending back direct, in situ measurements of interstellar space, and those measurements immediately began revealing things that models had not predicted. When Voyager 1 crossed into the interstellar medium, its instruments measured the particle density outside the heliopause and found it was 40 times greater than inside. That confirmed that it had genuinely crossed the boundary. But the details of what it found beyond that boundary have kept scientists busy for over a decade. In 2020, Voyager 1's magnetometer registered an abrupt jump in the intensity of the magnetic fields embedded in the interstellar plasma. At the same time, its plasma detector measured a rise in plasma density. Scientists believe those jumps were caused by powerful surges of plasma streaming outward from the sun that smashed against the boundary of the heliosphere, creating waves that reverberated through interstellar space, compressing interstellar plasma and intensifying magnetic fields far beyond the heliopause. The sun's influence reaching out beyond its own boundary and disturbing the space between the stars. Research published in 2026 using magnetic field data from Voyager 1's magnetometer through mid-2025 confirmed that Voyager 1 has not yet entered a completely pristine, undisturbed region of interstellar space. Instead, it remains in what scientists call the very local interstellar medium, a region still influenced, though weakly and intermittently, by the sun. The turbulence in the magnetic field has been gradually weakening, but it has not completely disappeared. Every year that Voyager 1 keeps operating and moving further from the sun, the measurements it sends back are the measurements of a spacecraft going deeper into truly undisturbed interstellar space, territory that no other instrument will reach for decades or centuries. Voyager 1 is also playing a role in understanding cosmic rays, high-energy particles that stream in from the galaxy and beyond. Because it is outside the heliosphere, it can measure the true spectrum of low-energy cosmic rays coming from the galaxy, without the interference of the solar wind that blocks those measurements from within the solar system. Data from Voyager 1 and its cosmic ray instruments, even through the end of 2024, has been providing a direct window onto cosmic ray transport across our region of the galaxy. With the cosmic ray subsystem now shut down, that particular window has closed. It cannot be reopened from Voyager 1. This is what is at stake. Every instrument that goes dark permanently removes humanity's only direct measurement of something in interstellar space. There is no replacement coming. No successor mission is currently funded or in development that would reach interstellar space within any of our lifetimes. The Voyager probes are it. They are the only ones out there, and they are running down. The Deep Space Network, the global system of large radio antennas that NASA uses to communicate with its deep space missions, has also been a constraint on the Voyager missions. The key antenna capable of communicating with both Voyager probes is Deep Space Station 43 in Canberra, Australia. According to JPL's announcement in May 2025, that antenna was offline from May 2025 through February 2026 for major upgrades, with only brief operational windows available during that period. The Voyager team had to plan all of its operations around that constraint, executing commands in limited windows, waiting longer for confirmations, managing a crisis on a spacecraft nearly 16 billion miles away through a communication system that was itself partially offline. The team did it anyway. They shut down instruments, managed the unexpected February power drop, designed the Big Bang procedure, tested it on Voyager 2, confirmed its success on August 4th, 2026, and are now preparing to apply it to Voyager 1. Now let's talk about where Voyager 1 goes from here, both literally and in terms of what the mission can still accomplish. Voyager 1 is currently traveling at about 38,000 miles per hour. That sounds fast until you consider the distances involved. At that speed, it takes about 17 hours to travel the distance from Earth to the Moon. The nearest star to our Sun is Proxima Centauri, about 4.24 light-years away. At Voyager 1's current speed, it would take over 73,000 years to reach it. Voyager 1 is not going to Proxima Centauri. It is not going anywhere in particular. It is just going. On November 18th, 2026, NASA has calculated that Voyager 1 will reach a historic milestone. It will be exactly 1 light day from Earth. That means the distance light itself travels in 24 hours, about 16 billion miles. At that point, every signal sent from Earth to Voyager 1 will take exactly 24 hours to arrive. Every response will take another 24 hours to come back. The round trip for any communication will be 2 full days. This will make Voyager 1 the first human-made object to reach that distance. Every command, every check, every confirmation will require 2 days just to complete. Susie Dodd, the Voyager project manager, described what that means. If she sends a command at 8 in the morning on Monday and says, "Good morning," Voyager 1, she will get the reply back sometime on Wednesday. That is the reality of operating a spacecraft at interstellar distances. After that milestone, Voyager 1 will continue moving outward, growing more distant every year. NASA's mission FAQ notes that the probes could remain within deep space network communications range until roughly 2036. That is the outer limit. After that, even the signal will be too faint to detect. When communication finally ends, whether because power runs out or because the signal becomes too faint, Voyager 1 will keep traveling in silence. It will carry with it the golden record, a 12-inch gold-plated copper disc containing sounds and images from Earth, greetings in 55 languages, music from around the world, the sound of rain and wind and surf, a mother's first words to a newborn child. It was included on the chance that someday, somewhere, something might find it. In about 40,000 years, Voyager 1 will pass relatively close to a star called Gliese 445. After that, it will wander the galaxy indefinitely. Millions of years from now, long after everything we have ever built has turned to dust, Voyager 1 will still be out there, a message in a bottle, cast into a cosmic ocean that has no shore. But right now, in August 2026, it is still alive. It is still transmitting. It is running on about 22 watts, less power than a typical household light bulb. And a team of engineers in California, working from decades-old documentation and a 2-day communication delay, just proved with Voyager 2 that they have one more trick to give it more time. The Big Bang is coming for Voyager 1. The thermal test is scheduled for the end of August. If it passes, the procedure will be performed in the coming months, and if it works the way it worked for Voyager 2, the most distant spacecraft in human history will keep sending back data from interstellar space for at least 1 more year. Possibly 2, possibly into the 2030s. Every day it keeps going is a day of data that no other instrument can provide. Every measurement its magnetometer makes of the interstellar magnetic field, every vibration its plasma wave subsystem detects in the gas between the stars, is irreplaceable. It is data from a place no one else is listening. The people who built Voyager 1 never expected to still be listening nearly half a century later. The engineers keeping it alive today were not born yet when it launched. They are working from old manuals, older hardware, and a communication link that takes 2 days for a round trip. And they are keeping it going. The next update, whether the Big Bang works on Voyager 1, will be one of the most important announcements in the history of space exploration. And if it works, there's one more thing that could happen. That shutdown instrument, the one that went dark in April, could come back on. Stay with the story. It is not over yet. If you made it this far, you already know this channel covers the real thing, not the clickbait version. Subscribe and hit the bell. The Voyager 1. Big Bang result is coming soon, and when it does, I will have the full breakdown ready for you.